Sorry. So Krishnamurthy, or DJ, as he's sort of called, is a staff scientist at Google Research, DeepMind, working on safe and reliable and trustworthy AI. His recent work has focused on improving safety and reliability of AI deployed in high stake applications like healthcare. And along with him, Vivek is also at Google Health. He is involved in advancing biomedical AI to scale up into world class healthcare applications for everyone. He has been building large language models, which have biomedical applications, and leads Google Brain Moonshot project. His recent development from Google have been in multimodal medical AI. So, welcome, Divjotham and Vivek. They are online, and if I'm, are you there, Divjotham? You there?
Yes, I'm here, and I think Vivek's here also.
Okay. Okay. Great.
Yeah,
Okay. Over to you. Thanks very much.
um, can you all see my slides? And can you hear me?
Yes. Yes, we can hear you.
Okay, great. Again, thank you so much for the introduction and for having me and DJ over here. It's a real pleasure and honor. And yeah, so I want to maybe set a little bit more of context around the research that we've been doing over here and my personal motivations for doing it. So I grew up in different parts of India, and during my childhood, like especially in some of the like more rural areas in North India and Northeastern India. And for me, what kind of struck was for most of the people in the nearby towns and villages that I was growing up in, um, like access to healthcare was a big issue. I knew like people, for example, the people who used to be maids in our houses, they'd never seen a doctor in their entire lifetimes. And so for me, that was always a problem that has motivated me, and like always wanted to do something about that. So a decade back in my undergraduate thesis, I built an app known as Ask the Doctor Anytime Anywhere. It was stitched up using old school machine learning technologies and a lot of rules, and so clearly it was not working well. But I'm delighted to say that the arc of progress in technology and AI in particular allows us to dream of this future where we will be able to put a world-class AI doctor in the pocket of billions of people worldwide. And so today I want to tell you more about some of our recent work at Google uh, on MedPalm, which I'll talk about a little bit more about this, which illustrate the capabilities of these systems towards that. And then in the second half of this talk, DJ will talk more about how we can ensure that these systems are safe and reliable so that we can really start deploying them at scale to billions of people. So without further ado, so MedPalm is our system or a large language model that we have designed specifically for applications in medicine. And the paper that backs this work came out as a preprint last December, and it was titled Large Language Models Encode Clinical Knowledge. And the idea of building large language models for biomedicine is not a new one. Several people have been doing this for years, and especially since the advent of transformer models in 2017, there's been increased activity in this space. But maybe what was missing is number one, benchmarks. So, as you maybe all are aware, in many ways, the modern deep learning revolution that began in 2012 was catalyzed by the development of the ImageNet dataset by Fefeli and others at Stanford. And in many ways, I think like the recent large language model revolution has also been catalyzed by benchmarks such as Big Bench, which allows us to like measure and benchmark progress over here. But unfortunately for medicine, there's no real such benchmark. And then the second thing over here is there are no good evaluation frameworks. And why that is important is because we as machine learning researchers, we like to move fast. And so we like to have like metrics that we can very quickly track and evaluate and move fast with. And so typically metrics like, log likelihood, or in case of natural language generation, BLUE or CIDR or whatever. But oftentimes what happens is these metrics are not reflective of performance in real world clinical applications. And as such, you may end up with surprises when you start deploying these models in the real world. And so what you actually need is a proper and holistic evaluation framework. And so in this paper or in this research, those were the two things that we set out to address. And in addition to that, the broader question that we had in our mind was, given that these large language models today are trained on internet scale data, do they encode actually clinically useful knowledge or not? And so those were like the key questions or contributions over here. And so when you're preparing benchmarks, the first question is, okay, what is the task? And so for that task, we decided to settle on medical question answering. It has been a long-standing grand challenge for AI. And so over here, you see a proposal from some very esteemed researchers at MIT dating back to 1986. A proposal for building a medical question answering system for clinical decision support. And so there have been several attempts over the last couple of decades and beyond in doing building up medical question answering systems, just because of the potential applications over here and the potential impact. And this is a particularly challenging task because answering medical questions requires not just good comprehension of clinical language and vocabulary, but it also requires recall of appropriate medical knowledge based on the context. And then you need to be able to manipulate and reason about that knowledge that you comprehend and recall to come up with the final answer. So this is a very complex task, and that's why in some further slides I'll show you where like some existing models before our work performed and why they were not particularly good. But then the second thing over here, or the nice thing about this, is question answering is very general. And so many things can be framed as like a question or an answer, or an instruction or an answer. And so it subsumes many different application scenarios, such as, for example, summarizing doctor notes, or in clinical decision support, or triaging of patients in primary care, and beyond. So the task is very general, and so that's why we decided to build on it. So now that we have the task, the next question was, okay, what are the data sets that we would use over here? And fortunately for us, when we looked at the literature, there were several efforts, especially from researchers at the National Library of Medicine in the US, who had put together various data sets spanning many different aspects of medicine. So some of these included professional medicine questions, such as the US medical license examination. Some of these included medical research questions, such as question answering on PubMed articles and abstracts. And another set of them included consumer medical question answering. For example, what would like a user who's looking for medical information say about medications or symptoms or diseases? What are the kind of questions that they would ask? And so, given that there existed data sets that spanned all these things, and we knew that large language models generally encode a lot of knowledge, so we wanted to ensure that the data set or the benchmark that we had is diverse enough. So we decided to bring all of them together. And maybe one area where maybe we did not see enough sample diversity was more in this consumer medical question answering realm. And so that's why we decided to contribute another extra data set that we sourced from Google search. And so this data set was basically a question of like medical information questions that people asked or searched on Google when they were looking for medical information, basically. So that was this benchmark called Multimodal QA, and in short, it spanned, as I said, professional medicine, medical research, consumer medical questions. It had some questions that required multiple choice answering, some which required long form answers, and then some of these questions were open domain where the answer could be anything on the internet, and others would be closed domain where the answer would be restricted to say like a PubMed article or something like that. So this was a very diverse benchmark, and so that was the one that we settled on. So now that we had the task and the benchmark, the next question was, okay, so before I go into that, here you can see some example questions that were there in the benchmark. So on the left, you see questions from Health Search QA, which is questions people ask on Google when they're looking for medical information. So you can see that these are all very short and precise, very similar to search terms that you would have. The one in the middle is also from the same domain. It's again consumer medical question answering, but this was in turn put together by the National Library of Medicine in the US. And one of the nice things about this data set was it also had reference answers that were curated by librarians who were looking at different sources of information, such as medical books or health articles and beyond. And then on the extreme right, you see a very different kind of question. So that question is coming from the US medical license entrance exam. So over here, you see a very detailed vignette with descriptions about a patient, their symptoms, their medications, and then the questions are typically around diagnosis or prognosis or treatment. And the USMLE exam has different steps, and so each step results in like increasing difficulty in general. And then it's also multiple choice answering, so it often involves the process of like deduction and logic and reasoning to come up with the right answer and eliminating the rest. So you can see that these are like very, very varied questions, and so it's very diverse, and it allows us to comprehensively benchmark the models that we have. So we have the task and the benchmark. And the other thing that I said that was missing was an evaluation framework. And so to allow us to like, comprehensively benchmark these models and evaluate them appropriately, we decided to do human evaluations. And for that, we had two different sets. So one set of axes was actually done by professional clinicians who had background in different specialties and training in different countries. And these professional clinicians, or these panel of clinicians, they were asked to rate a model on a bunch of different axes over here. So some of these corresponded to like factuality. So the scientific consensus one corresponds to that. And as you all know, hallucinations and factuality is a big problem with large language models in general. Others included, the potential of harm and bias in these answers. Again, that's a very important axis, especially in medical applications. And then we also had, axes pertaining to how accurately the model was comprehending the question, how was it recalling medical knowledge, and was it doing the reasoning appropriately or not. So these set of axes were evaluated by professional clinicians. And then we had another couple of axes that were actually done by non-expert users. And the reason for doing this is because we realized that oftentimes the end user of a large language model is not necessarily a clinical expert or a medical expert, but maybe someone who's actually not trained in medicine at all. So it could be like someone who's just looking for medical information, or maybe like a community health worker or something like that. And so for them, what we wanted to get out of them was whether they thought the answers were helpful and whether it directly addressed the intent that they had when they were asking these questions. So put together these two set of like axes corresponded our like was our evaluation framework over here. And so now that we have the the benchmark and the evaluation framework, the next part was, okay, what is the modeling looking like? And so in the original version of the paper, we decided to build on top of the Pathways language model from Google. I believe it's still till date the largest densely activated decoder-only large language model. And in particular, it has 540 billion parameters, the largest version of it. And it was trained using this system known as Pathways at Google, which is a very large-scale ML orchestration system that allows you to efficiently train giant multitask multimodal models on like thousands of TPU accelerators. And so the first thing we did over here was actually just take that model and evaluate it out of the box on these USMLE style questions. And the version of the model that we did over here was slightly different from the base model. It was called FlanPalm, and the only difference over here was actually instruction tuned, and that resulted in even better performance on some of these natural language tasks. But when we looked at the performance of these models on these USMLE style questions, we saw a significant improvement compared to the previous state of the art. And so, like researchers at Stanford and Microsoft and others had been like working on this problem for a couple of years prior to our work. And the performance in general was plateauing at around like 50% accuracy. But then we saw that, the FlanPalm model that we had, it immediately led to like a 17% improvement in performance. And it was actually the first AI system to achieve like a passing score equivalent or beyond on this benchmark. And the passing score in USMLE is typically around 60% over here. So that was great news for us. And then we looked at like performance on other MCQ benchmarks as well. And over there, again, the model was reaching state-of-the-art performance. And the Med MCQA dataset might be of interest because that comprised mostly of Indian medical entrance examination questions. So this was all great. And when we looked at like the performance of the model across different parameter sizes and different scales, what we observed was an accelerated improvement in performance as we started scaling these models. And so that kind of suggested that maybe the capability to reason about medical questions and answer them might be an emergent capability. And by emergent, I mean, the capability does not exist in smaller size models, but then emerges when you scale up the model beyond a certain number of parameters. This is a hotly debated topic in the field of LLMs and AI, but we seem to think that, okay, scale is important over here to, solve complex medical question answering tasks. So the question is then, okay, I mean, all this is great. The performance out of the box is great, and we had to do nothing. We just took a large language model, and that resulted in really good performance. And so the question is, are we done? And it turned out not quite. So when we did a human evaluation of the model responses, especially to the long form consumer medical question answering questions, that is when we saw or observed key limitations of this flan palm model. And so remember that flan palm does not have any medical domain training. It does not have any medical domain specialization. It's just a large language model that has been trained on a lot of data from the internet, basically. And so while out of the box on some of these MCQ benchmarks, it did really well. It turned out that when we did human evaluation on the axes that I talked about previously, the performance was not good. And I'll come back to detailed results in a moment. But what we then had to do was to actually specialize and align this general purpose large language model to the medical domain. But one challenge with medical domain is typically you don't have a lot of data because of different reasons such as governance and privacy and beyond and so forth. So what you need is a very data efficient specialization or alignment technique. But fortunately for us, while we were working on this project, there was another technique that was being pioneered at Google Research, and this technique was called prompt tuning. And what this technique does is it very efficiently allows you to align a model to the requirements of the domain and specialize it. And the way it works is it actually keeps the large language model for the most part frozen and introduces the small set of additional parameters that you can then train through SGD and backprop using small amounts of data. And in doing that, it is a very effective conditioner. And that in turn, significantly changes the behavior of these models and makes them more safer and accurate and beyond. So the technique does not introduce any net new knowledge into the model. And that was fine for us because just as we looked at the results on, say, some of these MCQ benchmarks on USMLE, it was very evident that these large language models, once you train on medical domain on the internet, they already encode a lot of medical information. So what you needed was more like shareability and teaching the model the requirements of the medical domain. And so to do that, the prompt tuning technique was actually very effective. And just to give you a sense of how everything came together, we actually just ended up using 100-odd examples that were crafted by expert clinicians. And these typically look in the format that I show on the left over here. So there's a question, and then there's an expert clinician response. And you use these set of question answers to basically learn these prompt parameters. And so on the right, you see that the blue part of the model, which is the base model, that's mostly frozen. And that's the billions of parameters that you have. And then you have the small set of additional prompt parameters in purple, and that is the one that we learn. And this overall technique, we call it instruction prompt tuning. And then once we do that, this resulted in this new model known as MedPalm. And the first question we had once we had this model was, okay, does this in any way affect the medical knowledge that is already encoded in the base model? And so to just check that, we once again evaluated on the USMLE questions. And what we observed that there was no drop in performance compared to flan palm on the USMLE style questions. It was just the same. And so in many ways, the medical knowledge encoded in the model was not affected at all. But what happened was there were significant behavioral changes on the other axes that we really cared about. And so, for example, when we looked at this axis on agreement with scientific and clinical consensus, and so this is basically seeing, okay, is the model hallucinating or is it generating factually accurate answers? And there we see a significant improvement. So when we looked at the base model flan palm, that was only producing factually accurate answers like 62% of the time. But then with this prompt tuning, we saw that MedPalm was able to get to pretty close to clinicians. Actually, it was getting factually accurate answers almost 93% of the time over here. So that is the exact kind of behavior that we wanted, and that was great for us. And this was again replicated in pretty much all the other axes that we had in our evaluation framework. For example, when we looked at the possible extent and likelihood of harm, again, we saw significant improvements. So flan palm answers were considered harmful like 25% of the time. And for met palm, that came down to close to 6%. That was almost on par with like expert clinicians. And similar performance again on the potential of bias in these responses. So flan palm responses were 8% of the time considered to have like some form of bias in them. For met palm, that was at 0.8%, and that was actually somewhat better than clinicians even. So that was great. And then when we asked non-expert like lay people regarding the helpfulness and the utility of these models, again we observed significant improvements compared to flan palm for met palm, but it was not quite good as clinicians. So you see that clinicians over here were getting like their answers were rated as helpful like 91% of the time, whereas for met palm it was only around 80%. But overall, I think this was a very helpful research for us. I mean, we had a very nice evaluation framework, and we saw that we had a very data efficient alignment technique that very quickly allowed us to build models that could potentially be useful. And so this was the first paper over here, and it was very recently, just last month, it was actually published in Nature. And so that was great for us, and that was the first milestone. But obviously, you need the performance of these systems to improve further and bridge the gap with clinicians. And so that was what our next paper did. And so this is where we introduced METPALM2, and over here we show that we were significantly bridging the gap towards expert level clinicians over here, at least in this medical question answering setting. And so under the hood for METPALM2, what changed was essentially we changed our base large language model from PALM to PALM2, which we at Google, we introduced at Google I/O back in May. Then the second thing that we did is we had access to more medical domain data. And so that allowed us to actually fine tune the language model end to end and not just use this prompt tuning technique. And so that turned out to be very helpful and effective as well. And the third thing that we had was a more, I would say, effective reasoning technique that allowed the model to do more deliberate system 2 style reasoning instead of just spitting out the answers like in a single shot that you would do in system 1. And so that in turn again also gave like performance boosts on these USMLE benchmarks and all the multiple choice questions. And then finally in the paper we also had more comprehensive human evaluations, and so we had an adversarial questions data set that actually looked at sensitive topics such as obesity, suicide, mental health, also COVID-19 and beyond. I mean, essentially topics where if the model produced any sort of medical misinformation, that would amplify existing disparities in healthcare. So we wanted to be very sure that the model was actually not doing any of that things. And so we put together this special data set that we have, and we call that break METPALM. And then we also had a side-by-side preference comparison study where we asked a panel of clinicians to rate between METPALM1, METPALM2, and physicians which answer they preferred, or like just do a ranking exercise over there. And so that was the overall contributions in the METPALM2 paper. And so very quickly, I want to maybe spend a couple of seconds on this idea of self-refinement. So it is this new prompting strategy that we introduce, and it's very simple. And so typically you can spend more compute by scaling up these models, but you can also have like a model size fixed, but do like repeated iterations in order to like get out multiple different reasoning paths from these models, and then kind of like marginalize over them to come up with the final answer. And so this is like more deliberate reasoning approach that you have, and it's kind of like similar to how, say, if you have a complex problem, you may want to like think through all the possibilities, and then like maybe through a process of deduction and elimination or whatever, you come up with the final answer. But what it encourages is the model to like not come up with the answer in just a single shot, but like think comprehensively through all the possibilities and reasoning paths that are possible before coming up with the final answer. And so we call this technique self-refinement. It's very simple. And so this is the prompting strategy that we used when we did our evaluation on all the MCQ benchmarks that we had. And very quickly summarizing the results that we had. So previously I mentioned that METPALM was around 67% on USMLE. Now with METPALM2, we were able to get up to 85%. And that was on par with expert test takers. And so it's another 18% leap. And all this happened over a span of like 3 months. And so that kind of tells you the pace at which AI is progressing in general. And then when we did the side-by-side ranking exercise where we compared answers from MedPalm 2 with physicians and MedPalm 1, we saw that for almost all the axes that we had in our evaluation framework, MedPalm 2 answers were preferred over physician answers. And again, on the adversarial questions dataset, MedPalm 2 answers were significantly better than MedPalm answers. So yeah, here's a very quick summary of the results. I'm not going to spend too much time on this slide over here, but feel free to check out the MedPalm 2 paper where we go into this in very comprehensive detail. And then, yeah, I'm going to skip these slides again for the interest of time. And then when we looked at like the non-expert evaluation, like when we asked again like lay people whether they thought MedPalm 2 answers were more helpful or whether they thought physician answers were more helpful, what we saw this time was actually MedPalm 2 answers were rated to be more helpful than even physician answers. So that's great. So what we were seeing is across the board, MedPalm 2 was actually bridging the gap and actually performing in many ways better than a panel of expert clinicians on the set of questions that we considered. So it felt like another big milestone for us in general. And in terms of like what were the differences in the responses, so here's an example question. You see that the MedPalm answer for this question, which is asking about a cure for typhoid, is very short, and it does not have any details and so on and so forth, and it's actually omitting important information. But then when you look at the MedPalm 2 response, it is very comprehensive, it is more factually accurate, and it is less prone to missing any sort of important information over here. And so that is the big difference that we saw in performance between MedPalm and MedPalm 2. The last paper that I want to very quickly talk about is our more recent work on MedPalm multimodal. And this in turn builds towards our vision of generalist biomedical AI systems. And the motivation for doing this is actually very simple. So if you look at medicine as an endeavor, it is a multimodal endeavor, and clinicians routinely interpret information from like so many different modalities, right? So you talk and language, but you also have like medical images, you have lab records, you have sometimes EHR, like health record systems, and vital signs from sensors, and you also have genomics information increasingly. And so you need the AI systems to be also able to like encode and interpret that information if they want to develop like a more contextual and holistic understanding of the patient. And so that is what we kind of wanted to build towards over here. And there are several approaches to developing multimodal large language models. But we decided to go after the most ambitious possible approach over here. And the idea that we wanted to build on and see if it was even possible was to train actually a single model to perform like many different multimodal tasks and encode information from multiple different modalities, all using the same single set of model weights. And so, and there are other approaches, for example, where you can like fuse together different you can fuse together a vision encoder with a language model, and then or maybe like use the abstraction of tools to build this. But we decided to go after the most ambitious version over here, because if this works, this is also the simplest one in many ways. And so, yeah, here's a very quick animation on the initial MedPalm M prototype that we had. So this model was able to not only interpret like clinical text, but it also was able to interpret, for example, medical images such as chest X-ray or dermatology skin images or mammography skin images. It was also able to interpret like pathology images and also genomics information, and all this using the same set of model weights. Very quickly, under the hood, the model is built from another embodied language model that we had at Google, which was actually originally built for robotics called PalM-E. And in the process of developing this MedPalm M model, we also introduced a new benchmark called Multimed Bench. And this is an open source benchmark that spans 7 different medical modalities and has 14 different tasks, spanning generative and predictive tasks, basically. And so the MedPalm M that we had, or the model that we have, it is actually it's actually the first demonstration of a single generalist biomedical AI system that with the same set of model weights can effectively encode and interpret data from so many different modalities. And one of the nice things about having this language modeling framework to build a multimodal model is that you can use language as a common grounding across many different tasks. And this in turn can lead to like combinatorial generalization. And so we observe very interesting capabilities such as zero-shot multimodal reasoning and generalization to novel medical tasks and concepts. And all this emerges from the fact that we were able to use language as a common grounding to interpret so many different medical modalities over here. Um, and then the last contribution that I want to very quickly highlight that we had in this paper was we also again did another human evaluation study, but this time we looked at the radiology reports that were generated by the model and compared that to reports generated by expert radiologists. And we saw that in over 40% of the cases, the MedPalm generated reports were preferred over expert radiologist reports. Uh, and further, we also observed that the number of clinically significant errors in a report was around 0.25, which was uh, at the same level compared to even expert human radiologists. So all that basically suggests that the system is already at a scale where it could be potentially viable in clinical applications, at least for radiology. So yeah, this is a very quick high-level overview of all the different tasks that we have and all the different modalities that we had. So on the left, you see, again, like the different medical modalities we had, like medical images such as mammography and radiographs. We had pathology images. We had genomics images, and we also had like dermatology as a task. And on the right, you see the different tasks that we have in the benchmark. So this included like medical image classification, but also radiology report generation and summarization. It included medical visual question answering, and also this task known as genomic variant calling, which is very specific to genomics. And then the figure on the right basically illustrates the increased capability that you have with this multimodal model. So we compared the model's performance to specialized models that were only trained to perform that single task really well. And so those are denoted by the red dotted lines over here, which are basically the spokes on the right. And you can see that for many of the tasks, compared to like these specialized models that you have, the MedPalm M model, which is a generalist model that's trained to solve all of them together at the same time, performs actually even better than some of the specialized models that you have without any sort of customizations. And so in general, the shaded blue area that you have, it's basically demonstrating the increased capability that you have with the system when you like expand the number of modalities that you can interpret and the number of tasks that you can solve. So yeah, and the last thing that maybe I'll very quickly highlight about the
Vivek,
MedPalm.
Vivek,
Yeah.
can I interrupt you? Sorry. I think DJ is also there with you who was
Yeah.
to present. Yeah. So if you can quickly wrap this up, or maybe I don't
Yeah.
know. DJ, are you there? You have DJ.
Yeah,
Um,
yeah, I'm here. But I think Vivek, why don't you wrap up with your section because I think we're kind of out of time.
Okay. Okay.
yeah.
Thanks.
So yeah, please refer to the paper for more details. And so I talked a lot about like the capabilities of these large language models. And I think now the next question is actually how to make them reliable and safer so that we can actually use them in real world applications. And so DJ is going to talk more about how we can do that. And so yeah, I'll just pass it on to DJ over here.
Thanks, Vivek. I think in the interest of time, I'm just gonna like say something very quick. Basically, we're building these very powerful AI systems, but it's clear that they still have limitations and they don't do the right thing all the time. And we need to think carefully about how to carefully integrate them into real clinical workflows. Without going into the details, because we're in the interest of time and letting us move on, I just wanted to highlight some work that we've done recently, saying that we can reason about when medical AI systems are unsure of their answers and when they would be better off deferring back to a medical expert rather than reasoning by themselves. And we managed to show the effectiveness of this kind of approach for a bunch of medical imaging diagnosis tasks, like detecting breast cancer from mammograms or detecting tuberculosis from chest x-rays. So I think, Vivek, you can skip to the last slide, and I think we'll just kind of end with a link to the paper. And yeah, thanks everyone.
Do we have any questions if for Vivek and Sorry, DJ. Sorry, DJ had a very, very brief, like 2 slide talk, but yeah, for Vivek primarily. Any questions? Yeah, Sam. Can we have a mic here?
Hi. A bit of a question in that, when humans ask each other questions, we first qualify why we're asking questions in the form of we figure out whether it's an expert or a fellow doctor. You try to make a large language model to decipher very many different use cases, all the way from novice asking questions to experts asking hyper-specific questions around detail. Would not it have been better to perhaps have some sort of primary, I guess, encoder at the front to classify different types of use cases, and then therefore the accuracy of the model would increase?
So I think that's the nice part about these large language models, in the sense that you don't need those specialist encoders or components anymore that you have to train. We have this phenomenon of like prompting or in context learning, where you can actually give these models language instructions and tell them about a task, and then they are able to very effectively adapt to that task or follow that instructions and then solve the task. And so there's no need for like any bespoke parts or encoders or whatever. And so that's, I think, one of the really nice things about these large language models within context learning, that allows us to like very rapidly solve like tasks that span like different settings. So it could be professional medical questions, or it could be like some of these non-expert questions. You just have to give them the instruction and say, for example, this is a question coming from this setting, or this is a question that you need to answer in this way, and they're able to very effectively follow that. And so I think that in turn is enabling the very rapid adoption and deployment of these models as well. And so that's the big change that we are seeing. It's just very easy to customize these models with just natural language instructions.
Okay. Thanks, Vivek. So.